Hello, welcome to the Points of Topology Live Session 6 NPTEL NOC course. This is Shovik and working on Lawrence Counseling by IIT Madras. So there is a sixth live session for this course. So before starting further, so there is one student, Mustaq. Okay. So Mustaq, can you please confirm whether I am audible and is the screen visible to you? Can you please confirm? Mustaq, can you please confirm whether I am audible and is the screen visible to you? Okay, I hope everything is fine. So let me start today's session. Okay, before starting further, let me okay. So I have shared attendance sheet Google form in the Google chat. Please submit this form for recording your attendance. Okay. So before going further, please let me know whether do you have any question or doubt from the previous session. If not, in that case, we shall go for some new things. So please let me know if you have any question or doubt from the previous session. I shall wait for 1 or 2 moments. In case you have any doubt or any question, please let me know. Don't hesitate. These sessions are taken only for problem solving purposes. So if you have any doubt or any question, please ask. Don't hesitate to ask any question. Okay. Okay, so it seems there is no question. So anyway, if you have any doubt, please ask. Okay, so let me start. Okay, so let me start with few definitions. So first definition is, so there is something called no, 1 minute. So there is something called total disconnectedness. Okay, so it is live session 6. What am I? What is not showing? Uh, so live session 6. Okay, so there is a definition. It is called totally disconnected. Okay, so the definition goes as follows. A space X, of course with some topology tau, is said to be totally disconnected if
Can you repeat this question again?
yes. So right now I did not start a question. So basically the thing is okay. Before going further, can you please confirm whether I'm audible and the screen is visible to you?
Yes, yes.
Okay, thank you for confirmation. So right now we are basically discussing what does it mean by totally disconnectedness, and then after going with the definition, we shall solve some problems. Okay. So right now let me write on the definition of the total disconnectedness. Okay. So X tau is a topological space said to be totally disconnected if the only connected subspace are singletons. This is by what we mean by total disconnect. That means singletons are the only connected subspace. So the exercise is that show that if X has discrete topology, then X is show that if X has discrete topology, then X is totally disconnected. So this is the uh, question you need to solve. Okay. So it's not difficult. Please try it. Please bear with along the definition. Think about it. Take your time. It is a very easy problem. Just it's a matter of applying the definition. Okay. So there is nothing to do much. Please do think and let me know the answer. So basically here what you need to show, you need to show the singletons only connected set. That means you need to choose a set which is not singleton and you need to show that it's disconnected. So that's what you need to do. Okay, think about it, take your time. So the hint is as follows. Basically, Hint is that isn't. Hold a moment, please.
No, it is now not audible.
Okay, how?
Please check.
How?
Please
How?
check.
Yes,
Hello.
yes. How it is not connected?
No, no. I tell actually the audio is not working.
Oh,
Now it is working.
okay, okay. Thanks. Okay. Okay, so the thing is that, uh, okay, so the idea is as follows. So start with any a sub of x. We start with any subset with number of elements at least 2. Okay, and then we need to show that s is disconnected. So how to do that? So we can take s, we can write s equal to, so since okay, so choose a s not belongs to s. So then s can be written as singleton s naught plus s minus singleton s naught, and both s naught and singleton s naught, these are open in s. So that means what? Because we have discrete topology. Why open? Because we have discrete topology. So that implies what? S is not connected. So that means what? We start with an subset S of X with number of elements of S is greater than 2. Then S is not connected. Okay. So that tells that the space with the discrete topology is totally disconnected. Okay. So that is the argument. So is it clear? Basically, what was the target? Our target is to show that if we take any set which has elements belonging to 2 in the discrete topology, in that case that S is disconnected. So that is equivalent to showing that our space is totally disconnected. So please let me know, do you have any question or doubt, or else we can go for the next problem. Please let me know, do you have any doubt or any question? If not, then we shall go for the next problem. Okay, so it seems this question is clear. So now let me go for the next problem. So the next problem is as follows. Mm, hold a moment. Yeah. So the next problem is as follows. Let me write it down. The next problem tells that let A subspace of X, okay, show that if C is a connected subspace of X that intersects both A and X minus A, then C intersects boundary of A. So if C is the connected subspace of X, if it intersects both A and X minus A, the it will intersect boundary of A. So that's what we need to figure out. I mean, we need to prove this, okay? So first try to do this by yourself, okay? Take your time. It is very, it is not easy, but it is not too complicated also. Take your time. Let me know. I shall back with a few minutes. Okay, so anybody able to solve this problem? Mustaq? Okay, so there is one more student. So are you able to solve the problem? Archer, are you able to solve the problem? Please let me know.
So just now I have joined, so I was thinking about it. I need some time.
Yeah, yeah, sure. Take your time. So what about Mustaq? Are you able to solve this? So the idea for solving this problem is as follows. We have some A, okay, and we have some C, okay. Now we need to show that if, somehow we need to figure out that if C intersection boundary of A is empty, then C can be written as, sorry, then C can be written as union of two closed sets F1 union F2, or union of two open sets F1 and union F2 which are disjoint, okay. So basically you need to find those closed sets or those open sets in order to conclude. So you can assume that the C does not intersect the boundary. So in that case, you can able to you shall able to get a disconnection for separation for C. So that's what you need to find out. Okay. So please try.
So in the question BDA, is that boundary of A?
Yeah, BDA means boundary of A. Correct.
Okay, sir.
So any idea how to approach this? I mean, I will give you the hint. Anybody? Please unmute yourself and tell me the solution.
I have no idea, sir.
Sorry, I'm unable to hear you. Can you please repeat again?
I have no idea, sir. Can you give me any clues?
Yes, yes, sure, sure, sure. Take your time. Take your time. Okay, the argument. So let me explain the solution. So first of all, boundary of A, that is A closure minus A interior. It can be written as A closure intersection X minus A whole closure. Okay, this is the first thing, and this is a well-known thing already. You can find it in a textbook. Okay, now we can define F1 to be C intersection A closure and F2 to be C intersection X minus A closure. Okay, and of course A closure and X minus A closure are closed set, so both are closed in C2. Okay, now the point is that since boundary of A, I mean, now the point is that um, we need to show that C is equal to F1 union F2 and as well as F1 intersection F2 empty. This is what we need to show. Okay. Now, first of all, so first of all, observe that now C is equal to C intersection A closure union C intersection X minus A closure. That is by construction. That can be written as C union of, sorry, C intersection of A closure union X minus a whole closure. Okay. Now, the point is A closure union X minus a whole closure, that is always equal to X. The point is you can check it directly, so there is no confusing it. There is no confusion or there is no complicated way for doing this. It is very direct, pretty direct. Okay. But now, if A closure intersection, okay, so now if we assume now C intersection A closure intersection C intersection X minus A closure, that could be written as C intersection of boundary of A. Okay. So if this is empty, then that implies what? That implies C disconnected. But it is in the question is given that C is not disconnected. That means what? This C intersection boundary of E, this is non-empty in actually. So that's what the argument is. Is it clear? So basically what we are doing for solving this, we are only choosing F1 and F2. One is A closure, another is one. So we are choosing basically one is A closure intersection C, another is X minus A closure intersection C. Okay. And finally, we are showing that those union is C and their intersection is empty if the C intersection boundary face is empty. So that tells that C is disconnected. Is the argument clear? Please let me know.
Yes, sir.
Thanks. Okay, so the next question is, just hold on. So there is some interesting question. So there is some combination. There is some interesting question. Let me get back with this book. Hold a moment, please. By the way, go to the Google chat. I have, let me share you um the Google form again. So I have shared the Google form in a Google chat. So you can submit the form for mocking attendance. Please don't forget. Okay, so okay, so the next problem is mm, next problem. Hold on. Okay, so the next problem is as follows. Let XD be a metric space. Assume it is connected. Show that if X has at least 2 points, then X is uncountable. So basically what you need to show, you need to show that, okay, instead of uncountable, you can let me write it as infinite. So this theorem tells that if a metric space and if we assume that is connected metric space, and if X has at least 2 points, then X is infinite set. There is infinite number of elements. Okay. So okay, so let me okay, first think about it, take your time, then I shall give some hint. If you please first try by yourself. So please try, do try, or else I shall give some hint. Any idea how to solve this? Any guess? Okay, so let me give you one hint. So it is given that x has at least 2 points. Okay, we can choose 2 points x naught x1 belongs to x, and these are not equal. Okay, now you can create a function f from x to r with x going to d of x naught. It's a distance function. Okay, and it is known to be continuous, so there is nothing to check really. Now use the fact that x connected. Okay, so this is the hint. So basically observe that f of x not equal to 0, but f of x1 is not 0. That means image of f contains at least two distinct points in R, but image of s is connected. So from that, what we can say? Please think and let me know. Okay, I shall be back with a few minutes.
So I can use the theorem that the image of a connected space under a continuous map is connected.
Yeah, continue, please. Continue, please. I'm audible.
The image of a connected space under a continuous map is connected. So I can tell that the image of the given function is connected.
Hmm. Correct, correct. Then that means you are saying that image of f is connected, right?
Yes, sir.
Okay, after that, and also image of f, it contains at least two elements. Is that clear? Is that clear why image of f contains at least two elements?
Because the cardinality of x is greater than or equal to 2,
Hmm.
I'm taking the image from that connected space. So it also need to be uh, also have at least two elements. Can't be one or empty set.
Please repeat the argument again. Why it will have two elements?
The cardinality of the x is to greater than or equal to 2.
Correct.
I'm taking the function from that connected space, so
Hmm.
it can't be one or an empty set.
But the point is that the function image, it can be singleton also. Singleton set is also a connected set, right? Correct. So you,
But I'm taking the image as the distance between 2 points, right, sir?
yeah, right.
So how can it will be one?
So I mean, my question is that what are those? I mean, give me two distinct element of image of f. That's what my question. Give me two distinct element inside the image of f. I mean, you need to show that image of f contains two distinct real numbers, right? So what are those? Are you understanding my point?
Can you repeat it, sir?
Yeah, we need to show that image of f contains at least two distinct real numbers. So what are these?
Is that x naught minus epsilon and x naught plus epsilon? I'm not sure. I'm just guessing, sir.
Fro- from where the plus is coming?
What?
From where you were saying now that is it? Didn't you say x naught plus x1?
No, sir. X naught minus epsilon and x naught plus epsilon.
X naught is an element in the metric space, right? So how you can take x naught plus epsilon or minus epsilon, right? These are not real number, correct? So see, the point is already we have given the fact that x0 and x1, these are two distinct elements within x, right? And the function f is distance function, correct? So that means what? F of x0, it is nothing but d of x0 x0. This is 0. And okay, and f of x1 is equal to d of x1 x0. This is non-zero. Why? Because x1 not equal to x0. So that means what? 0 and fx1, these are two distinct elements in image of f. Is it clear? Is it clear? That means,
Yes, sir.
so this tells that image of f contains at least 2 points. So that is the first thing. Okay. Now the point is that image of f is also connected subset of R. So that means what? Image of f is an interval. Is it clear that in real line the connected sets are only interval? Is it clear that in real line why connected sets are only intervals? Yes or no? Is it clear that why in real line connected sets are only intervals?
Can you explain it why, sir?
Yeah, the point is that it is a fact in real analysis that it's a fact actually. It is not immediate. Okay, in the course real analysis you must have seen this, or else you can find it test. We will see this. The point is, let a subset of R.
Using Hein-Borel theorem.
No, nothing like that. It is a fact in real analysis, so it has nothing to do with it has nothing to do with the Heine-Borel theorem. So the fact is that if A is a subset of R be connected, if and only if A is interval. So it is a fact, and you definitely have seen this in metric real analysis course. Okay, so that's what the thing is. So image of f, so due to this fact we can directly tell the image of f is an interval, and interval is always infinite, so that tells what? Image of f infinite. So that implies domain of f is infinite, otherwise image of f would be finite, right? So that's what the argument is it clear? Is this argument clear? Why the domain of f is infinite?
Yes.
So, okay, so this tells that if we have a connected metric space, in that case, if it is at least two elements, then this will be infinite set. So this is one problem. And the next problem is, hold Okay, so the next question is as follows. The next question, let me write it down. Does there exist continuous function f from R to R which sends rationals to irrationals and irrational to rationals? Sorry. So does there is a continuous function f to f which sends rational numbers to rationals and irrational number to rationals? Okay. So okay, so please try. So for this also you just connectedness, and you need to use the trick of as of the previous problem. So please try. Any idea how to solve this, or how to approach, or I mean, or any guess?
I think the image will be an interval.
Ima okay, so image will be interval. Then what? Yes, image of course will be interval. Correct. Very good. Then
Because if I choose any interval in R, that interval will have rational as well as irrational. So I think I have to find an interval as an image of that function.
uh, okay. So first of all, the answer is that it's such a function does not exist. Okay. Now try to prove that such a function does not exist.
So it will exist when f from R to R cross R, sir.
Yeah.
I mean,
Yes. Tell me. F of. I mean, it does. Such a function can't exist.
yes, sir. If it exists, means my function should be in R to.
The function is from R to R already, right?
Yes, sir.
Yeah. Then whatever thing I'm unable to figure out, can you please read again? Please do.
You are telling that such function will not exist.
Correct.
I'm asking that when will it exist?
I mean, such a thing can't exist. So there is no condition when it will exist. It can't exist. Such a function can't exist. That's what the question is. I mean, the existence, the non-existence is not unconditional. The point is, if it is continuous, then such a function cannot exist.
If I change the domain and codomain, will it exist?
I mean, if you change the domain and codomain, then different thing will happen. But if you change the domain and codomain, then you can't talk about rational or irrational, right? We can talk about rational, irrational only in R2, only in R only, right? Inside R2, we can't talk about that, correct?
Yes, sir.
So now try to show that such a function can't exist. Okay, take your time.
Can I use method of contradiction?
Sure.
Sir, any hint?
Yeah, continue. Any idea how to approach? No need to hesitate. You can whatever you in your mind you can tell. Okay, so let me explain. The argument is as follows. So first of all, since f continuous, so that means f of r, this is uncountable by the previous argument. Why? Because intervals are uncountable. Okay. Now, given the fact that its f sends rational to irrationals and irrationals to rationals. Okay. Now q is countable, set of rationals is countable. This implies what? This implies f of q is countable. And also f of r minus q, which is sub of q, is also countable. That tells what? F of q union f of r minus q is countable. But f of q union f of r minus q, this is nothing but f of r. But already we have seen this f of r has to be uncountable. So that is why f of r countable, it's a contradiction. So that's why such a function can't exist. Is the argument clear? Please let me know. Is the argument clear? Please let me know.
Yes, sir.
So let me go to the next problem. So the next theorem is as following. The next exercise is as following. This exercise is that let x d, not xt, just let x be a topological space such that for any two points x, y, x, there exists a connected subspace A of x, which contains both x and y. Show that x is connected. The property is that suppose x topological space such that if you take any two points from x, then there is a connected subspace for any two point which contains those 2 points. You need to show that x is connected. Okay. That's what I need to show. So please try. So directly, okay, so the hint is that you can use the function method. That means what? You need to start with an arbitrary function from x to plus minus 1. I need to show that this function is constant. Okay, so that's your way to show. So take your time, think about it, let me know. Let's try. Can you please try, or can you please explain at least how to add this? I mean, you need to start with some function from x to plus minus 1, and to show that it is constant. So that's what we need to show. For that, you need to use the given hypothesis.
So can you repeat it again?
Yeah, you need to show using function method. That means what you need to do, you need to show that choose an arbitrary f from x to plus minus 1 continuous. You need to show f is constant, and that tells that x is connected. Okay, so that's what you need to prove. Any guess? Okay, so let me explain the solution. See, so choose x naught belongs to x and assume okay, so basically what you need to show for showing x is constant, what you need to show, choose arbitrary x y belongs to x, and we need to show that f of x equal to f of y. Okay, now by the hypothesis, there exists a connected set A which is sub of x and which contains both x and y. Now consider the restricted function. In this function, this a is connected. Okay, so that implies what? That implies f restrict to a is constant. Okay, so that implies what? F of x equal to f of y. So this is the argument. Is it clear? Please let me know. Is the argument clear? Please let me know.
Sir, can you scroll the screen before?
Is that fine?
Yes, sir.
Okay.
If you don't mind, can you explain this again, sir?
Yeah, sure. So, what? Yeah. So, in order to show connectedness, here we are using the theorem that we choose a function here from x to plus minus 1 continuous, and we need to show that f is continuous. That will tell that if that will tell that our space x is connected. Okay. So, in order to show f is continuous, what we need to do? We need to choose basically the equivalent showing that if we take to any arbitrary points x and y, then we must have fx equal to fy. Okay. Now the point is that the hypothesis of our question tells that if we take any 2 point x and y, then we'll get a connected set A which is sub of x with xy belongs to A, such that A is connected. Okay. Now our function was from x to plus minus 1. We restrict the function on A to plus minus 1, and A is a connected set. Okay. So f restricted to A is a constant function. So that means what? Fx equal to fy, because x and y are the points in A. So that's the argument. Is that clear? Or any portion we are unable to understand, please let me know.
Yes, sir. Clear.
Okay. Okay. So the next problem. Hold So so next question is that show that R2 minus a point is connected. And then if we extract a point from R2, it will be connected. Please try to show this. I mean, intuitively it is clear, of course, but you have to prove it mathematically. Or instead of random point, you can take the point 0. So that means show that R2 minus 0 is connected. Let's not take random point, it's a specific point. Now please try to prove that.
It is already known that any continuous map f from x cross y to plus or minus 1 is constant. So, um, to show that R2 difference singleton 0 is connected, I have to show that any continuous map f from R cross R difference 0 to plus or minus 1 is constant.
Correct. So how to show that? So see, you have one information that R2 is connected. Of course, R2 is connected, okay? And but you have a function from R2 minus 0 to plus minus 1. So, hmm, so what you can say about that? Or instead, okay, or without using the fact that R2 is connected, you can also directly show that R2 minus 0 is connected by using this function method. Try to do that. I mean, in the previous problem, we have restricted the given function to some connected subspace, right? So you need to find R2 minus 0, but in R2 minus 0 there is many disconnected parts. Sorry, in R2 minus 0 there are many connected subspace, correct? So try to use that. Try to argue visually at least.
Sir, if I take any 2 points from R2 different singleton 0, like x1 comma y1 and x2 comma y2,
Okay,
mm, that 2 points will also be in R2.
correct then.
I already know that R2 is connected. So, using the previous theorem, I can tell that R2 different singleton 0 is connected.
Okay, so can you please explain how to for any 2 point we can get a connected set containing those two? Can you please explain? Can you please explain that why if you choose any 2 points, then those 2 points are contained into connected subspace? Why? Can you please explain? Can you please explain once again? Okay.
So here some sound is audible. So
No,
I can,
you please tell the argument once again.
I will be taking 2 points from R2 difference singleton 0. Um, the 2 points will be an ordered pair x1 comma y1 and x2 comma y2.
Correct then.
Then by the previous theorem, there exists R2 in which these 2 points will be in R2 also, but I don't know why I'm telling like that.
The thing
Um,
is that
I don't know why. What is the reason for the necessity to have the 2 points in R2?
I mean, what do you mean by what is the necessity to have those 2 points in R2? Because the domain, because we want to show that R2 minus 0 is connected, right?
Yes, sir.
That's what we want to show. So that's why we are choosing the points from R2 minus 0, correct?
Yes, sir.
And maybe I interpreted wrong your question. Can you please repeat the question? I'm unable to understand what does that mean.
You're asking that um, why the connected subspace should have those 2 points, right, sir?
Correct, correct. I mean, my question
I,
is that yes,
I don't know what is the reason.
Look at the previous problem. In the previous problem, what we have seen? We have seen that if we have a topological space and if it has a property that if you take any 2 points such that there is a connected subspace, then the whole space is connected. This fact we are trying to use for our problem R2 minus 0. So basically what we want to show that if we choose two different points from R2 minus 0, then we wish to find a connected subspace R2 minus 0 containing those 2 points. Is it clear?
Yes, sir.
Okay, so now please try to attempt.
I already know that R2 is connected.
R2 is connected, yes, correct.
So I'll be telling that these 2 points will be in R2 also.
Yeah, fine. Then you need to find a connected subspace within R2 minus 0, right? The subspace can't go outside R2 minus 0, right?
Okay, okay, sir.
Yeah, yeah. Okay, please try.
Can I choose that connected subspace as n crossing?
N cross n. I mean, n cross n, these are just discrete points, right? I mean, these points lies in certain distance. So these are not connected, of course, right? N itself is not connected, correct? See, the idea is that, I mean, the point is, one minute. If we have 2 points, this x1 and x2, hold on. Just hold on. If you have 2 points here and here, okay. I mean, the point is you can consider straight lines passing those 2 points, correct? If you have point this and this, you can consider straight line passing those 2 points. So if you choose any 2 points and if the straight line don't pass through the origin, then the straight line lies within the subspace, correct? And if suppose we have 2 points here and here, and suppose this line passes through origin, so for that, in that is what you will do, you will choose another point outside here and you consider this line plus this line L1 and L2. In that case, L1 union L2, this lies inside R2 minus 0 and containing those 2 points. So in that way we can confirm, we can say that R2 minus 0 satisfies the property that any 2 point is contained in the connected subspace. Is the argument clear? Please let me know.
Yes, sir.
Okay, correct. Okay. So that's what the question was. Okay. And okay, now using this, can you show that S1 connected? Either you can use this or without using this also you can show. um, why does not opening? Okay, so show that S1 the circle is connected. So that circle is connected. It will be easy, so it will not be difficult actually. Please think and let me know. So for this you need to use the continuity technique. Okay, so I mean you need to find a continuous function f from some connected set to S1 such that image of f is some S1. Such a thing you need to do. Okay, so that's what the process. You may think later on, so no issues for that. Just hold on. What happened? Okay, so is it clear the way of solving this problem? Is the way of solving this problem clear?
Yes, sir.
Okay. Okay, so in that case, it is 8 now. So let's stop here. So if you have any doubt, you can drop an email or you can ask in the next session. Okay. So I'm leaving the session now. Thank you.
Thank you, sir.